Hello class, my name is Tina Carter and I will be teaching you this semester the course Abstract Algebra. The text is Contemporary Abstract Algebra by Joseph Gallion, and I was able to get copies for each of you. So if you drop by my office sometime this week, you can pick up your copy of the text. A little about myself. I live in Buffalo, New York, and my husband and I are both visiting the University of Hyderabad this semester. We are supported by Fulbright Nehru grants, so I'm really looking forward to spending this semester with you. My grant proposal involves a new pedagogy called Flipping the Classroom. So that's what I'd like to try this semester. What that means is that I will provide you these videos as lectures and ask that you watch them at home and take a good set of notes. Then during class, we're going to work together on problems, which will usually be, or quite often be, proofs. They require writing skills, and I think that we could develop that in the classroom together better than having you work on it alone at home. So I hope that you will enjoy this. My videos are not professional, as you probably already have realized. All I do is record the regular lecture that I would give in the classroom. I asked for our class to be split into two sections so that it would be easier to work with you during class individually on the problem sets that I bring in. I hope that you will feel comfortable with this and freely ask questions of me during class or during my office hours. Abstract algebra is at its heart the study of mathematical structures. Informally, you can think of a mathematical structure as a set with one or two binary operations defined on it. For example, you are familiar with the set of real numbers with two binary operations, addition and multiplication, defined on that set. And you are very comfortable working in that set. In abstract algebra, we're going to look at mathematical structures or sets, and we're going to define operations on them and see what structure the operations induce. In the real numbers, for example, you know that the operations addition and multiplication are both commutative operations, and that we have the distributive property that associates addition with multiplication. I think the best advice I could give you for doing well in this course is to try to forget a lot of the stuff that you already know. Open your mind to thinking abstractly and using only the definitions and theorems that we prove in class. You use them as tools. It's critically important to know all the definitions defined in the lectures and that you read in the book, to know them word by word, and then you will be able to use them in discovering new things about the algebraic structures that we study. As you will see in the textbook, the first thing that we need to do is discuss some preliminary topics, things that you are already acquainted with, but again, making sure that you understand the correct notation and the definitions involved. First of all, some sets of numbers. The natural numbers we denote with capital N, and using the proper notation, we would say N, the natural numbers, is the set of numbers 1, 2, 3, and so on. The integers we obtain from the natural numbers by throwing in all of the additive inverses of the natural numbers and the number 0. We denote the integers with a capital Z, and we can list them this way. Minus 3, 0, 1, 2, 3, and so on. The rational numbers are not so easy to list like we have done in the above two sets, so we will just use set builder notation. They're denoted by Q, and they are the set of all fractions, A over B, such that A and B are integers. This little thing that looks like an epsilon here is an element of. A and B, the numerator and denominator, are both integers, and of course the denominator B is not equal to 0. The real numbers are all decimal numbers. You probably remember that the other way that we could define the rational numbers is that they are all repeating and terminating decimals. Repeating or terminating decimals. So the real numbers are all the repeating decimals and the non-repeating decimals, in other words, the irrationals. So the real numbers are composed of all the rational numbers and the irrational numbers. The repeating decimals and the non-repeating. And these, by the way, are denoted by capital R. The complex numbers are denoted by capital C, and they are the set of all A plus BI, such that or where A and B are real numbers. And of course, I is the square root of -1. A prime number is an integer greater than 1 that has divisors only 1 and itself. Now keep in mind, I know that you all know what prime numbers are, but the important thing in this class is to know how to say it and how to write it. So if you are given a prime number in a problem, the first thing you think of is this number is an integer. It's greater than 1, and the only divisors it has is 1 and itself. Always think in terms of definitions. And another set that I know you are familiar with is the set of n by n matrices, like the set of all 2 by 2 matrices with real entries, and we will denote that as capital M in the subscript n by n. That is the set of matrices, square matrices, with real entries. We're going to review some properties of the integers. The first one is the greatest common divisor of non-zero integers a and b. We're going to denote this by the GCD of a and b, the greatest common divisor. For example, find the GCD of 396 and 154. Well, the best way to do it is definitely prime factor the numbers if they're big like this. So 396, if you break that down into its prime factorization, is 2 squared times 3 squared times 11. And if we prime factor 154, we get 2 times 7 times 11. Now you can see the factors that they share. They each have factors of 2, but the GCD will be equal to 2 times, well, they both have a factor of 11. So the GCD of 396, 154 is equal to 22. So you just prime factor the numbers and you look for the common factors. The greatest common factor, or the greatest common divisor, is 22. Now, the important thing about the greatest common divisor is that it can always be written as a linear combination of A and B. So how do we say this? You're going to need to be able to write things like this mathematically. So let me show you one way to write this. If, let's say, let D be the GCD of A and B. There exists, I'll use a backwards capital E to mean there exists, integers x and y such that, that symbol will always mean such that, D is equal to AX plus BY. That's what a linear combination of A and B looks like. I'm not going to show you in this lecture how we find X and Y. It's based on the division algorithm and the resulting Euclidean algorithm. You can check that in the book if you're interested. But in our example up here, I'll just show you, and you can see for yourself, check, that 22 is equal to 2 times 396 plus negative 5 times 154. The least common multiple of integers A and B is denoted by the LCM, least common multiple. The least common multiple of A and B, two integers. I think it's self-explanatory what that means is the smallest multiple of both of them. So again, you would look at the prime factorizations, and now we would have to include all the prime factors of both of the numbers. So in this case, looking up there at the prime factorization, we have to have 2 factors of 2. We have to have 2 factors of 3 squared. We have to have a 7, and we need a factor of 11. So this would be the least common multiple. Euclid's lemma is something that you'll find handy in our study of the integers. If P is a prime number and P divides A times B, then P divides A or P divides B. If you're not familiar with this notation, that vertical line means divides. So before we start a proof, you always take note of what tools you have. We know that P is a prime number, so that we know P has no divisors other than 1 itself. And we know that P divides AB. Well, how do we write that? P divides AB. Or let's just give a general note here of what it means for P to divide any number, any integer. If P divides X, that means that X is equal to P times something, let's say Py, for some other integer, y. So we'll need that, and now let's try to prove Euclid's lemma. Let's see, P is a prime number and it divides AB. We want to show that it divides either A or B, so let's just suppose that P does not divide A. So then we wish to show or prove that if P doesn't divide A, it has to divide B, that P divides B. In other words, we're going to be looking for something where we can say that B is equal to P times something. That will mean that P divides B. All right, so P does not divide A, means that the GCD of P and A is equal to 1. And this allows us to write 1 as a linear combination of P and A. Let's write Px plus AY. Well, we want to have B being P times something, so let's multiply through by B. So B is equal to PBx plus ABY. Well, I can see that we're almost done here because P, here I'll write it out, P obviously divides PBx, and since we were given that P divides AB, we know that P is a divisor of ABY. So P divides this term, P divides this term. We know then, therefore, 3 dots in the corners of a triangle mean therefore we have proven that P divides B, and we're done. A generalization of Euclid's lemma is, and you will use this often, if P divides the product A1, A2, A3 up to A sub n, then P divides A sub I for some I. It divides at least one of the factors. Now, is this true if P is not prime? Maybe you want to put this on pause and try to answer it yourself. Look at this example. If we know that 6 divides 10 times 3, 6 divides 30, but 6 does not divide 10, and 6 does not divide 3. So this Euclid's lemma only is true for prime divisors. Another property of the integers is the well-ordering principle. And it's obviously true. If every non-empty set of positive integers has a least element. Think about it and make sure that you see why. We're going to use the well-ordering principle to prove the fundamental theorem of arithmetic, and that is that every integer greater than 1 is either prime or a unique product of primes. There's actually 2 parts to the proof. We're just going to show that every integer greater than 1 is a product of primes. The proof of uniqueness you could look up yourself online. So we're just going to prove the existence of a prime factorization. And this will be a proof by contradiction. So we're going to start by supposing that this is not true. Suppose not. Well, then that means that there are some integers greater than 1 that is not a unique product of primes. And since that is a set of integers greater than 1, we know that it contains a least element. So we'll say suppose not, then let n be the smallest integer greater than 1 that is not a product of primes. Suppose not. Well, then we know there's a smallest, and we can say that this number n is either prime itself or not prime. That's true of any integer. It's either prime or not prime. Well, clearly, if n is prime, we're done. And since n is the smallest integer greater than 1 that is not a product of primes, then really we don't have to consider this first part. N is clearly not prime. If it was, it has a prime factorization, just itself. So n is equal to a times b, for some integers a and b, both greater than 1. But a and b then are both less than n. So a is equal to p1, p2, product of primes up to p sub k, let's say, and b is less than n, so we know that b has a prime factorization. Let's say it's q1, q2, up to q sub s. Well, then n is equal to p1 times p2 up to p sub k times q1, q2 up to q sub s. And we have contradicted our assumption that n was not a product of primes. So we can conclude by saying this contradicts our assumption, and therefore n, all numbers greater than 1, all integers greater than 1, are either prime themselves or they do have a prime factorization. The division algorithm is something you've used since elementary school, but we need to be able to state it formally so that we can use it in our study of abstract algebra. Let a and b be integers with b greater than 0. There are unique integers q and r, well, that's just quotient and remainder, where the remainder is greater than or equal to 0 and less than b, which was the divisor. And of course we write that as a equals bq plus r. For example, if a is 42 and b is 11, we're dividing 42 by 11, and we say 42 is equal to 3 times 11 plus 9, so the remainder is 9. If we were dividing 11 by 42, we would write 11 is 0 times 42 plus 11. Notice the remainder is positive and less than 42. If a is equal to negative 6, then we want to write a equals negative 6 is equal to minus 2 times 5, which gives us minus 10 plus 4. So in each case, the remainder is less than the divisor. In some mathematical systems, we're only interested in the set of possible remainders. For example, what time will it be 50 hours from now? You don't count up 50 hours. You think this way. You think, well, 50 is equal to 2 times 24 plus 2. So this is what you concentrate on, is the remainder. It'll be 2 hours from whatever time it is now. So we're dividing by 24 and throwing out the 24s, and we're just looking at the remainder. This is called modular arithmetic. And what we mean here, or what we will say, is 50 is equal to 2 mod 24. Another example you use all the time, what month will it be 50 months from now? Well, we know there's 12 months in a year, so we're thinking, although we certainly don't write this down, we're thinking that 50 is equal to 12 times 4 plus 2. So we just ignore the 12 times 4, and we say, well, it'll be 2 months from now, or March. What we're saying here is that 50 is congruent to or equal to 2 mod 12 arithmetic. In these modular systems, we only have the possible remainders upon division by 12, 0 through 11. Up here, 50 is equal to 2 or congruent to 2 mod 24. Well, in this number system, we're just looking at remainders upon division by 24. And here it is said more formally. A is congruent to B, or sometimes you could put equal to B, if A and B leave the same remainder upon division by n. Or equivalently, and notice that this is true in our examples, A is equal to B, or congruent to B mod n, if and only if n divides their difference. For example, 121 is equal to or congruent to 13 mod 3 because 3 divides their difference. 121 minus 13 is 108. We could say that 121 is congruent to 13, but I would rather say 121 is congruent to 1 mod 3. In other words, bring it down to the remainder that is less than 3, because 121 minus 1 is 120, which is divisible by 3. So let's practice just for a minute computing modulo 5. 14 mod 5, well, divide 5 in, we see we have a remainder of 4. 14 mod 5 is 4. 12 times 13 mod 5, well, you could multiply 12 times 23 and then divide by 5, but we can write 12 is equal to 2 mod 5, and 23 is 3 mod 5, so we get 6 mod 5, and that is equal to 1 mod 5. So 12 times 23 is 1 mod 5, or we can say 12 times 23 modulo 5 is 1. Here we have a difference mod 5. Again, there's no need to compute the difference first. You can actually take the equivalent numbers mod 5 and then subtract. So we see that 112 is 2 mod 5, a remainder of 2, and 93 would leave a remainder of 3. So we get negative 1 mod 5, and we want to put that into a positive number less than 5, which is 4. That's because of the little equation that I've written here in red. Now, 21 to the 40th power. Here we do not want to reduce 40 mod 5. Leave the exponents as is, but 21 to the 40th we could write is the same as 1 to the 40th. We can reduce the base to mod 5. So that's the same as 1 to the 40th, and of course 1 to the 40th is 1 in any modular system. So that's equal to 1. 32 to the 41 mod 5 will be, well, we'll mod out 5 in the base, and we have 2 to the 40 power 41. And we can't change that to be, we can't mod out 5 in the exponent. So we'll try a different trick. Watch this. 2 squared, well, that's 4 mod 5. I'll multiply it. Let's square that again. So we get 2 to the 4th then. 4 times 4 is 16. That's 1 mod 5. And as soon as we found a power that's equal to 1, well, we can keep squaring that, and we get 2 to the 8th is 1. 2 to the 16th is 1 times 1 times 1 is equal to 2 to the 32 is equal to 1 mod 5. So I'll write 2 to the 41st power then as 2 to the 32nd power times 2 to the 9th. Oh, that's 2 to the 32nd power times 2 to the 8th times 2. Well, these powers of 2 are all 1, so our answer is 2. I could either write the mod 5 there, or I can just say 2. So this is the end of the first lecture. It's just properties of integers that we need to know for upcoming chapters. So I've written in red here the topics that we covered in this lecture, and you should come to class prepared to answer any questions about those topics.